Our lesson for today is going to discuss designing screws and fasteners. In engineering, these are very important because we're talking about joints that you can easily separate, put together at will, depending on the what you want to use them for or the application. So let's start with the usual introduction stuff. So when you talk about screw joints, we say that they're commonly used where you may need to occasionally separate the joints and put them back together, assemble, disassemble, and meaning that in most cases you find that you have a bolt and nut making up such a joint. And and of course, we're also saying that they come with threads. These threads also have their own advantages because they're easy to assemble. And they come with already established standards, so you don't have to start looking around for what can fit where. The standards have already been adopted. And it's also very easy to adapt them to various opening and closing conditions, unlike other types of joints. And they are also reliable, not very costly. If you talk about the disadvantages, the first one is that you see threads wearing out because where you have the threaded part, that is where the stress concentration is high. So as a result, you have certain types of failure coming there. And you cannot just pick any jam and jack to make a thread on a component. You need some skill as well as specialized tools for that. Terminology is used. First, we have the major diameter. The major diameter is this diameter we see in the diagram from the crest on top there to the crest on the other end. So all that is like our overall diameter. So this is basically the largest diameter of the thread, or the nominal diameter. The minor diameter, also known as the root diameter, is that diameter running from the bottom of the thread up to the other end. So from the root of the thread to the other root on the other side, this is our minor diameter. So this is the one labeled there. Pitch. The pitch diameter, of course, we're saying that the diameter of an imaginary cylinder on a cylindrical screw thread, the surface of which would pass through the thread at such points as to make equal the width of the thread, the width of the spaces between the threads. But then, this is the one that makes it complete, the pitch. So the pitch, you're looking at a thread at one point, you identify maybe it's the crest. The distance from that point to the next corresponding point along the axis on the same thread, that is on the next thread, that is our pitch. The lead, that is the linear distance now, the distance between two corresponding points on the same helix. Of course, it's supposed to be along the axis. Crest, that's the top of your thread. The root, that's the bottom of the thread. The depth of the thread is the distance, of course, from the top to the base of the thread. From the crest to the root, what you have sticking above the root there, that is the depth. Angle of the thread, this is where you see the flanks coming together. The angle between them gives you the angle of the thread. The flank is more like a face. So joining the root and the crest, that space in between, that's the flank. Basically giving you the side. So what about the forms of threads? We have various types. Some are called British Standard Whitworth, which uses thread angle 55. The same BSW thread, you can have one that is used for precision measurement instruments. Basically, this one now picks up another name, BA thread. American National Standard thread. This one has flat crests and roots. And of course, But they have also been able to work better than the V threads because of their flat ends there. The U thread comes with an included angle of 60 degrees. Then you have the square thread, which is one making up the shape of a square, both for the bottom and for the top, like you can see there, making those squares. Of course, we expect it to be weaker than the V thread because of the shape, but it's very good for power transmission and where you need a lot of lead to be covered. Fastenings, we have through bolts, we have tap bolts, studs, and many more. Now let's get to work. We have what is known as the initial tension when you are tightening a bolt, the initial tension. So initial tension, which is given by Pi, is equal to, or rather is given by 2840D, where D is the diameter of the bolt, the nominal diameter in millimeters, and that force will be in newtons as well. So Pi, that's the initial tightening or initial tension. D, nominal or major diameter. No confusing this with the root diameter, which you measure from the root of a thread, but we're talking about that diameter between the crests as you look at the size of this thread. Then we proceed. What about the safe axial load given by P? This one is the stress times the stress area. And here the stress area is normally concentrated around the roots, because if it has to fail, that's where things will happen. Sometimes this can also be used where you find the average, the pitch diameter plus the core diameter of the root diameter divided by 2, giving you the average squared over 4. Then you get the area. But you'll notice that when we're getting to the stress area, we'll just use this by dc over 4 by dc squared over 4, because that's where the stress concentration is highest. And failure usually begins from there. All right, so torsion stress due to tightening. So for torsion, we go back to the torsion equation. So like we did earlier, the first two sets, T over J, is equal to 2 shear stress over D. If you make shear stress the subject, we have T by D. Here we're talking about the core diameter or the root diameter over 2J, just everything else making shear stress the subject. So this is my grade. So if you go ahead again and expand J, the numbers will cancel out, then you remain with 16T over pi D cubed, taking us back to that expression we had earlier. The expression that we had used in the previous topic on shafts. So here, this is the torsional shear stress, so basically just the shear stress. Then DC, that's the core diameter or the root diameter. T is the torque applied as usual. So then, if you want the torque, the shear stress, you can also use the standard formula. Stress is force over area, where this is the area, this is the force, or the shearing force. And then if you come down there, you have, oh, sorry, let me just put some out. This is our core diameter, the width of the thread, and N, the number of threads. So then that's how you may find that. It's the same thing we're seeing here, except just use the different value for B, or for D, because this is now for the nut. And that one was for the screw. For the nut, we're using the core diameter. For the screw, we're using the nominal, the major. Crushing of the threads due to compressive stress. So here, it means you find that force responsible for crushing, then divide by pi d squared minus that d squared, then n, where of course n, that's the number of threads, then the core diameter, and d is the nominal diameter or the major diameter. So this is our compressive stress. The bending stress, this one becomes a bit interesting because we have a special formula now where we say bending stress is equal to x multiplied by E over 2L. X is the difference between the extreme corners of the nut or head. E, that's Young's modulus, then 2, of course, the number L, that's the length. Now, when you're tightening a bolt, you are basically applying external forces. The stress due to external forces, therefore, the tensile stress comes in. So, of course, there we're saying this is the root diameter represented by DC. Then stress T, that's the tensile stress. Therefore, P, which is the force due to the same tension, is supposed to be the area by the stress, by the tensile stress, by the cross-section area. The cross-section area we're talking about is for the root. So we say pi d squared over 4, where d is not for the major, but the root, because we always say stress is force over area. When you make force the subject, you multiply this whole expression for area by the tensile stress. So in case you have a lot of bolts, then you just introduce letter N to represent the number of bolts. In the case of shear stress, again, say D, our major diameter, N, number of bolts. Again, it's the same thing. By d squared over 4 multiplied by the shear stress, we include N for the number of bolts. Where PS, that is the shearing force. What if we decide to combine them? Then it means we go back to those expressions. Maximum shear stress is equal to half tensile stress squared plus shear stress squared 4 under the root. Then go back to the maximum principal tensile stress. This is where I have stress 2 over 2 plus half under the root of tensile stress squared plus 4 shear stress squared. Let's now do the application. Example 1 says we have two machine parts fastened together tightly by means of a 10mm tap pot. If the load tending to separate these parts is neglected, calculate the stress that is set up in the bolt by the initial tightening if the core diameter is 8.16 millimeters. So the major diameter D is 10 millimeters. The core diameter or the root diameter is 8.16 millimeters. So then let's find the stress area. For the stress area, we are going to use this, like we say, this is the problem area. So we use the same formula where stress area A is equal to pi d squared over 4. But D is the root diameter, the core diameter, the diameter at the bottom of the thread, at the base of the thread. We were given that this, in this case, it's 8.16. So we square it, divide by 4. Then it is equal to 5.23 by 10 power negative 5. Our answer is in square millimeters. So 5.23 multiplied by 10 power negative 5 square millimeters. Let's go to the initial tension. The initial tension P is 2840D. 2840D. So given that our D is 10 millimeters, then this is the constant number. So multiply 2840 by 10, we get 28,400. So with that, we now proceed and just say tensile stress is force over area. So we bring this number on top and then the area below. So here we have 28,400 divided by 5.23 by 10 power negative 5. And then the tensile stress becomes 543 megapascals. 543 megapascals. Let me just try to emphasize here. There are two parts. We have the major diameter as well as the root diameter. How do we use them? The whole secret is in the way we handle the data. You can see that the core diameter is here, and that's the one we use for finding the root, or rather the stress area, because this is the area of concentration of the stress. Having done that, it means this diameter has done its job. We can now turn to this other one here. So with this comes now the initial tension. The initial tension does not use the root diameter. It uses the outer diameter, rather the major diameter, the nominal diameter, which in this case was given as 10. So this is the standard number, the standard formula using 2840 multiplied by the diameter, which is 28,040, rather 2,840 multiplied by the diameter, the nominal diameter, which is 10. Then our answer comes out as 28,400 newtons. What if you're now trying to tighten? Stress due to tightening. So then we go back to the formula for stress, which is force over area. Load, the stressed load, the tensile load, divide by the stress area. So the tensile load is 28,400 divide by what we got as the stress area was 5.23 by 10 power negative 5. So with that, we ended up with 543 by 10 power 6, which is 543 and 6 zeros, and therefore it's 543 megapascals. 543 megapascals, or simply 543 newtons per square millimeter. Let's pick up the second question. Here it says, we have two shafts connected by means of a flange coupling to transmit torque 50 Newton meters. The flanges of this coupling are fastened by 6 bolts of the same material at a radius of 50 millimeters. If the allowable shear stress for the bolt material is 55 megapascals, calculate the size of the bolts. Data provided, the torque is 50 Newton meters. So that's 50 Newton meters. But we want to work in millimeters, and we'll see why this one should be able to work out that well. So we convert 50 Newton meters to 50 Newton millimeters. We just multiply by 1,000. So we have 50 times 1,000, which is 50,000. Number of bolts, 6. The radius. A flange, of course, is basically just a wheel. At the center, to where the bolts are, the radius, we are told this radius from the center of the flange to each bolt, this R, we have been told is 50 millimeters. So RP, that's our 50 millimeters. Shear stress is 55 megapascals, or you can say 55 newtons per square millimeter. Let's pick up our solution. First, let's get the torque. Given that kind of information, the torque is simply force times radius. So if we want to find the shearing force, we'll make it the subject. It's supposed to be torque over that radius. So then our torque is 50,000 divided by 50. So here you can already see when I cancel this and this, and we'll also end up dividing this, it's 1, and also cancel that, it's 1. I'll end up with 1,000. That is my force. So going back to the formula we talked about, we say the shear stress, rather the shearing load, the shearing force, PS, is by d pi, the core diameter squared over 4, multiplied by the shear stress by the number of bolts. This is the core diameter. This is the shear stress. That is the number of bolts, and this is what we are from calculating. We can substitute and try to make core diameter the subject. So here is 1,000. Then we have pi times d squared over 4. The shear stress we're told is 55 newtons per square millimeter. N, the number of bolts is 6. Then the 4 still remains where it is. So here, when making D the subject, you remember to get the square root of what will be on the other end. And look at that. Our answer in millimeters comes out as 1.964 millimeters. Now this one comes with using standard tables. Meaning from there, when you compare that, you find that this number we've just found is corresponding to M 2.2 metric diameter, 2.2 millimeters. That is our answer. So this part is supposed to work in conjunction with the standard table, which has to be provided. I think in the notes, I'm going to plant it there so that you are able to refer to it. There goes our exercise as per tradition. And feel free to get in touch should you find where we need some clarity.